Hey friends, it has been again. This is a video for the Calc 3 class. You may recall that we had some examples that we did not finish in class concerning joint probability distribution functions, or JPDFs. So keep in mind the notion with these is that we've got random variables X and Y that are related to each other according to some function that gives you an idea of where the numbers will end up being, okay? But although they say that they are random variables, we actually have some ideas about their randomness. You know, they're not uniformly random. You have not equal probabilities you will end up anywhere, but rather there may be a larger probability you get a small number or a large number or something in the middle, just depending on what the functions are. The thing that I said in class is all that stuff is just kind of messy and maybe not much fun. Wouldn't it be great if we just did math with it? So bear in mind your joint probability distribution function is just any function that has an X and a Y in it, whatever variables you happen to be using. But it gives you an integral over its support. The support, remember, is the region where it's non-zero, but it gives you an integral over the support that turns out to be 1. And that was nice because then you didn't have to divide by anything at the end. And it has to be non-negative. You can have these vast regions where it is 0, but there has to be some region where it's, you know, non-negative, and that's what we refer to as the support. Okay. So we are going to look at exercise, hell, I don't know, I think it's exercise 9. Yeah, that's it. And we will figure out the details going on in this, right? So sharing screen, and let's get that going here. No, okay. Yeah. All right. Yeah, we are broadcasting from the glamorous location of my back porch. And so when I tried to share screen, it looked as though I might have ended up sharing to the TV screen downstairs. So I don't think it did, but you know. All right, so the problem from your sheet there is talking about the joint probability distribution function, and it's giving the lifetime in months of 2 components in a device. This is a fictional problem. It's just something that's an excuse to have us doing math, okay? But you have the lifetime in months for 2 components in a device, and we're going to calculate the probability that both components function for at least 12 months without failing, okay? And the joint probability distribution function that we're given here has, I think that's a 9216 in that fraction there. Let me peek over here at a different source, and I don't have a different source open. So let me just check on this real quick. File, open recent, the 224 handouts, applications. Yes, that says 9,216. All right. So then I have lost the window that I was sharing things through, so I have to reshare. Sorry if that gets annoying. But here we go. All right, so that number down there is indeed 9216. So What we need to look at here is our support region and see what it looks like. And then we're going to have to talk about this event here and figure out what that region is for that. Sketch it, and we're going to set up the integral. I might pause and try to figure out how to do the integral on GeoGebra. Yeah. So, all right, let's see how this goes. So here we've got if the x is greater than or equal to 0 and y is greater than or equal to 0. So we're in the first quadrant. And then we've got this 2x plus y is less than or equal to 48. If you solve for the y, you'll have a slope of -2. Okay. So just getting us a super rough sketch here. We've got the y-axis, we've got the x-axis, and we're wanting to think about stuff in this region. But we need to draw this line that has a slope of 2 and a y-intercept of 48. So rough drawing there. Doesn't have to be very exact. Keep that sort of thing in mind. And let's see, I'm going to put right here that 48 is that y-intercept, and in case it comes up, that 24 is the x-intercept. And then I suppose I could take and kind of, I don't know if I should bother shading this in, but kind of get that vague idea that we're talking about this region that's inside there. Okay. All right. So that is what we're going to think about with the support. And because I'm lazy about making up names, I tend to use an S for support. Then at least 12 months without failing. And it's both components function at least 12 months. All right. So that suggests that we have to have both X and Y. So I'm going to call my event T. So I'm going to say X needs to be greater than or equal to 12 and Y needs to be greater than or equal to 12. So that means I'll need to draw a line where X is equal to 12. Looks like it'd be about there. And my drawing may not be super great here, but Y equal to 12. And I started to label that wrong. X equals 12. Y equals 12. And we might want to check and see about that intersection, the point 12, 12. Check and see whether that is going to be in our support or not. So if you check that, you're just checking 2 times 12 plus 1 times 12, and that's 36, which is less than or equal to 48. So yeah, it is. Okay. And then I'm going to take and color in a little bit darker our region that we've got in here. Oh, and I made it too much. So bear with me, because I'm just trying to make it look a little bit darker. Okay. So we are going to want then to do our double integral over T of our P of XY dA. Okay. And so the setup on that, integral, and what was that P of XY? That's, so that horrible big number there, I'm just going to go ahead and refer to that with a C because I don't want to write it over and over again. But 48 minus 2x minus y d, I'm just going to go dy dx. If you want to go dx dy, have a field day. But because of the fact that we already did this thing here of solving and getting y equals 48 minus 2x for the top of the region, seems like that would be good enough justification there. So our x values, remember we wanted to start at 12, and then we are going to have to think about this to see where this ends up at. And of course, since you know the y value is 12 there, you can figure out that point by plugging back into the equation we've got of 2x plus y equals 48. So I will take the y out there and put a 12 in, subtract 12 on both sides, get 36, divide by 2, and it's 18. All right, so my x values go from 12 to 18, and then my y values will go from 12 up to the y equals, what was it, 48 minus 2x. Okay, so from that point, you're just doing a basic integration here, and I don't want to bore you with that. So what I'm going to do is to cheat and hit pause. Oh no, actually, why don't you hit pause and you do it? Go ahead and use the calculator or GeoGebra, whatever you want to use for it. But I'm going to go ahead and pause and come back with it solved. So, and I didn't hit pause, I rather hit stop share. So now I'm going to pause. Hey friends, I'm back. And let me share screen again with you. And hopefully you all have gone ahead and done the calculation as well. And I'm just going to sort of point at it a little bit here. I believe where I left off, we had gone ahead and done the setup for it there. And then we had to integrate with respect to y and plug these two values in for the y. And I got a horrifying mess when I did that. But then when I told GeoGebra to simplify my horrifying mess, it turned out to be 2 times the quantity x minus 18 squared, which of course you can do a really simple u substitution on that. And it's just a u substitution in power rule stuff. So the number you end up with out of that is going to be 144. Multiplying by that c, which, as you'll recall, is this 1 over 9216 up here. And so you get 144 divided by 9216. Gosh, I probably should have gotten like a better fraction for that. But insofar as an approximation, it's about 1.5%. So let's see if I do a better thing there. I'm going to totally cheat and pause for just a second, again, because of the fact that I can't do the numbers in my head, and I don't want to bother you with watching me do arithmetic. So so I jumped aside and did that real quick. It would be nice if I could pause while showing that screen, but I haven't figured that trick out yet. So anyway, we end up with 1/64, which is about 1.5%. Okay. So the event that we're talking about here is, relatively rare. Okay. I left a blank page here, thinking I might need some more to do the work, but then I didn't do it all by hand. I just went ahead and let the machine do it for me. All right, so this exercise 10 here is something that a lot of your authors' exercises will end up doing, of asking you to find a constant so that you make this into a valid joint probability density function, okay? So when you're tackling this, the thing I always do is to sketch my support and then set up the integral over it and just find out what I get. So with regard to this, it does say we want both x and y to be greater than or equal to 0. So we're in the first quadrant, and we want to be under the line. Didn't draw that very well. Okay, we want to be under this line here of 1 minus x. So if we go ahead and make 1 be both the x and the y intercepts, we've got a slope -1 and stuff. So y equals 1 minus x is that portion there. And if you want to do so, you might come in here and just kind of color it in. I always feel a little bit goofy when I'm coloring in these regions and using the highlighter, because it feels like I'm literally doing the whole thing with a crayon and stuff. So, all right. So we've got our support there. And so we're going to do the double integral over the support. We don't have to do the integral over anything else because the probability density function that you're working with here is going to be 0 everywhere except the support. Okay. So this means we can see from the picture that our x's go 0 to 1 and our y's will go 0 to 1 minus x. And in this region, we're getting the cxy, and then we'll say dy dx. Okay. And so c integral 0 to 1. I'm just going to go ahead and do this in front of y'all. Sorry if that's at all annoying, but x times 1/2 y squared. The y evaluate from 0 to 1 minus x. I will put some brackets in there. And the dx, c integral 0 to 1, quantity 1/2 x times 1 minus x squared. And when we plug in 0, we'll just get 0, so we don't care about the rest of it. So then times the dx, and it would probably be convenient here to be expanding that all out and have the 1/2 x cubed minus 1/2 of the 2x squared, so just x squared, and then plus 1/2 x dx. When you're integrating polynomials from 0 to 1, it's pretty nice because you can just say 1 over the power, and so we will have times 1/4 and minus 1/3 plus 1/2 times 1/2. So that's c times 1/8 and 1/4 minus 1/3. So 3/8 minus 1/3. Goodness. So 9, let's see in front. 9 minus 8, 24. So it's c times 1/24. And since you know that that needs to be equal to 1, because that's our purpose here with this joint probability density function, the c needs to be 24, not 4. All right. So, and like I say, typically that will be the first step on one of these problems, that you'll get a c value. and you just have to figure out what it's going to be in order to make the problem work out right. And then you just store that number as the C value and don't write 1 over 9,216 100 times, just write C 100 times. So, or hopefully you won't write it 100 times. Anyway, though, so those were the 2 examples I meant to get through in class. And I will see you all on Wednesday. Change variables.